Hey everyone, so in today's video we're going to talk about slope fields and Euler's method. So hopefully you remember a little about slope fields. They're kind of derived using a differential equation. In this example we're going to use dy dx equals 2y. So it looks something like this, where the slopes at each point don't really care about the x value, but as you increase in y they get steeper, and as you decrease in y they get, well, negative and steeper. So hopefully you remember that to actually draw a solution curve to this differential equation, we needed an initial value. So let's say our initial value was something like 0, 1 right here. Then a potential solution curve just by eyeballing it would look something like this and like that. Boom. And hopefully you do know that the solution to this equation, given that we have the initial value of 0, 1, is going to be e to the 2x. But let's just assume we don't know that for now. In fact, it'll be even helpful even if we do know it. We're going to learn about something called Euler's method, because just drawing these curves is great and all, but it doesn't exactly give us an exact idea as to what's going on here. So Euler's method does that for us. Euler's method is what's called a numerical method. Numerical method. Basically what a numerical method means is that we use numbers and approximations to basically work our way through things that are a little bit more complex, like e to the 2x, something that we can't calculate using things we can calculate using approximations. So let's go over how this works. First off, you start with an initial value, x and y. In our case, it's going to be x equals 0, y equals 1. Okay? Now, how this is going to work is we're going to take little jumps along the x. So we're going to take small little jumps along the x, and then we're going to calculate what dy dx is, and we're going to increase in y. Take another little jump in the x, find the y. Jump, 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 and eventually we'll get these lines that kind of give us a good idea of what the curve should look like. In fact, will give us actual values on the curve that are approximated. So how do we do that? Well, kind of the first step is just saying, let's just choose a delta x. Let's just say that dx should be about, I don't know, like 0.1. And hopefully you recognize that the smaller dx goes, the better our approximation gets. In fact, if it goes to 0, or a limit that goes to 0, we get the actual derivative. So that's kind of what's going on behind the scenes here. But if you choose a smaller dx, you're going to get a more accurate approximation. Larger dx, less accurate. So let's see how we do this. We've set our dx to equal 0.1. We want a couple other things to calculate. We want to calculate dy dx. And we also finally want to calculate dy, or delta y. Okay, dy dx is easy. It's just going to be 2 times our y value at any point. So let's fill that in 2. dy, let's think about our equation here. Dy dx equals 2. Well then, if we do multiplying over by dx, we get dy equals 2 dx. Luckily, our dx is set to be 0.1. So we just get 0.2 over here. There you go. What this means is, well, now we increase x by delta x, and we increase y by delta y. Basically, the idea behind that is if we start with a point and we're going to another point, well, our function, our approximation, is telling us, okay, well, we already know we're doing this set amount of dx, which is 0.1. And we're calculating dy using the slope field in our differential equation to be 0.2. So we know, okay, we go over 0.1, up 0.2, and we get our next point, 0.1, 1.2. Now repeat the process. dy dx is 2 times that, which is 2.4, times 0.1 is 0.24. So now we increase x by 0.1, increase y by 0.24, multiply by 2, divide by 10, and then add on another row. So part of this is it's kind of a lengthy process and it's a lot of math, but you will be expected to do a lot of this algebra that might be kind of annoying. So it's good to practice your algebra skills. 3.456, 0.3456. And then finally, we're going to stop here at 0.4 equals 2.0736. Okay. So let's see what we've actually done here. Let me make another graph here. So let's have that be 1, that be 2, 1, 2. So we start at 0, 1. Then at 0.1, we're at 1.2, which is about here. 0.2, we're at 1.44, which is about here. 0.3, we're at 1.7, which is about here. 0.4, we're about a little bit above 2, so let's say right there. Hopefully you see, and let me make this one a little bit more accurate. There, or like there. You see that it's kind of following this line, or this function right here. And luckily, if you do enough of these points, you will see that it follows the function y equals e to the 2x. Now, like we said, this is approximation. This is a numerical method. It doesn't exactly follow e to the 2x, but it's pretty darn close. In fact, we can actually check how close we are. So, whilst e to the 2x might be really hard to calculate, we can use Euler's method to approximate it. Luckily, I can just use my calculator right now to see the values we get, but let's see. So for actual e to the 2x, these should be our points. So you have 0, 0.1, 0.2, 0.3, and 0.4. We get 1, 1.22, 1.49, 1.82, and 2.23. Compare this to our approximated values. 1, 1.2, 1.44, 1.73, and 2.1 about, or 2.07. So as you can see, I mean, it gets worse as you go on, of course, because each time we're kind of we're underballing, you know, what the actual curve is for e to the 2x if you try to imagine this process. So we're kind of getting worse and worse as we go on. But as you see for the first couple of values, I mean, 1.2 is a pretty good approximation of 1.22. And so is 1.44 of 1.49. So in general, these approximations are pretty darn good if you do a small enough dx, of course. If you did even smaller, it would be even better. If you did larger, it probably wouldn't be that great. So Euler's method, you'll be expected to do this kind of table right here, which is what I would recommend you try out. In fact, as an example, I want you to start with the initial value of 0, 1. And I want you to use a delta x of, let's say, 0.2. And I want you to use the curve e to the x, or in other words, dy dx equals just y. And I want you to approximate what E is, or Euler's constant, or 2.71828. So use the exact same process we did up here, where you start at 0, 1, write out your delta y, dy dx, calculate delta y, add on your values each time until you get all the way to 1. And once you get to 1, you should then know e to the 1 is hopefully a little bit close to 2.71828. It's not going to be perfect, but try it out. So hopefully that was helpful as an explanation of Euler's method and slip fields.